Good day to everyone. So in the last video we have seen about the torsion of the cylinder, and we have derived the expression for the torque per unit twist and the related problem we have solved. So today we are going to see about the determination of rigidity modulus with the static torsion method. Okay. So determination of rigidity modulus and we have used the static torsion method. So in this method what we are going to do is we are going to take a long cylindrical wire, and one end is fixed with one rigidly fixed with one part, and in another part we are going to attach a wheel, and with this wheel we are going to add a weight, so that when we are adding the weight, the wire will be going to be twisted, so that the wire going to be experience a torsion. So we are going to find out what is the torsion. Okay. So this is the apparatus which we are going to use to calculate the rigidity modulus of the wire. So this is the wire which is this is from A to B. This is the wire which we are going to use to calculate the rigidity modulus, where the one end is fixed with the one end of the wire is fixed in the position A, and another one end of the B is fixed with the wheel. So this wheel is actually connected with the weight, so that you can add the weight here with the corresponding the weight, so that you can calculate the mg, that is the force acting on the wire. So once if you are continuously adding the weights, the wire will be twisted. Okay. So the twisted is actually calculated in the this scale. This scale is actually with measured with marked with the angles. So without the weight, it actually the apparatus actually adjusted to have the 0 degree angle. So once if you are adding the weight, so that there will be some torsion experienced in this wire, so that this needle of this two ends will be slightly move in the left side. Okay. So the angle of twist can be measured by means of the 2 points, which we can take it as this is Q and this is R. So where we are going to measure the angle of twist measured in the scales. So this measured the twist in terms of degrees, which we have to convert it into the radians. Okay. So with no weight added on the hanger, the initial readings of the pointers on the scales are adjusted to be the 0. Okay. So once you are adding the loads in terms of every constant addition, suppose if you are taking the some m grams, the m kilograms, so you are actually adding the m kilograms each and every time. For example, suppose if m is equal to 0.5 kg, that means half kg, then you have to add the every 0.5 kg for the each and every reading. Okay. So first we are going to add the 0.5 kg, then we are going to measure what is the reading in the scales Q and R. So we are actually having that some tabular column where we are going to retake the readings of the Q and R, and the readings in the two scales. Maybe this is taken as a S1 and this is taken as a S2, so that you are measuring the angle, the deviation in the angles in the Q and R for the 0.5 kg. Then you are going to add the 5 kg, 5 more kg, so that for the 1 kg of weight, what is the twist which we are going to calculate it again for the both scales. So similarly, you are adding the 0.5 kg each and every time. So you are calculating the twist. So you can take the readings for at least 10 to 15 addition of weights. So the readings on the two scales are noted for every load, both while loading as well as unloading. So once you are taking the readings for the loading the weights, and then the same after that you are going to unload the weight with the minus of 0.5 kg, and you are going to measure the same deviation in the opposite direction of the two scales. Okay. So once you are done with the loading and unloading in the one direction, that means on this direction, you are going to take this rope on the other side, and you are going to twist the wire in the clockwise direction. So initially you are actually taking the torsion in the anti-clockwise direction. So in this direction you are going to twist it by adding the weight in this side. So once if you loading and unloading readings are taken in this direction, then you are going to take this full hanger on the other direction. So you are going to now adding the same weight on the other direction, so that it means you are going to rotate the wire in the clockwise direction. Then you are going to take the same readings while both loading as well as unloading with the equal weights. Okay. So all the observations are tabulated in the specific table. Then the readings in the last column given the twist for the load of some mkg. For example, the load is given as sometimes m into some mkg. The total weight we have added is a mkg, and suppose you are measuring the length of this distance from Q to R, that can be taken as length. Which is equal, that means in the from Q to R, which is taken as the L of the rod. You can also measure the radius of this wire with the screw gauge, so that you can find the radius. You can find the diameter, and then you can find the radius, which we can take it as a of the rod, and and then you can taking the radius of this wheel also, which can be taken as the radius of the wheel, which taken as a capital R. Okay. So the load of mkg is actually suspended on the free end of the wire, and the twisting torque can be written as m times m into g into the radius of the wheel, so that I can take it as the twisting torque is equal to mg into the R. That is what the force given in this direction. It is we already seen that the force F into R is the twisting torque. So we already have the measured the angles, that is the twist angle, the twisting angle, which is actually taken as a theta in terms of degrees, so that you can just convert this into the radians. This is in degrees. Then you can convert this theta into radians, so that you can just multiply with the pi divided by 180, so that you will get the corresponding radians. Means you have converted the measured angle in the radians. So if you know all these things, then we can know the restoring torque. That means we already derived this restoring torque. So the restoring torque can be written as pi g a power 4 theta divided by 2L. So this theta in terms of degrees, or if you are converting it into a radians, then you can multiply with the pi by 180. So this is the restoring torque. Okay. So suppose if the twisting torque and the restoring torque is equal, then we can equate these two equations, that the twisting torque as well as the restoring torque. So for equilibrium, at equilibrium position, then I can equate this mgr is equal to, that means the capital mgr, which is equal to this torque. Okay, I can write this as pi g a power 4 theta, this is pi divided by 2L into 180. Okay, so I can just multiply this to 180 divided by 2. So I can take it as maybe I can just take this pi as pi squared, and 360 into L. Okay, sorry, not degree. So 360 L. Okay. So from this I can easily calculate what is the rigidity modulus, because I know we can easily calculate the rigidity modulus G, because we already know how many kilogram weight we have added G is a constant, R is we have already calculated, that is the radius of the wheel, and A is the radius of the circle, the cylinder, the cylindrical wire. Theta, which we already measured, the L is also we know, so that we can find out the G, that means the rigidity modulus, which is equal to 360 m G R L divided by pi squared a power 4 times of theta. Okay. Now we know what all the values, all the quantities in the right hand side, so that we can find out the rigidity modulus. So this is the formula to calculate the rigidity modulus using the static torsion method. Okay. So the only thing which we have measured, we are careful about this is we can see that this the radius is in terms of so the fourth power of the relation, so that whatever you are measuring in the theta or m, the kilogram, everything should be very accurate, because a power 4 is it's very accurate. Okay, so you have to measure, so while calculating the radius of the wire, we have to be very accurate. Okay, so while doing the experiment, we are going to have two approximations. That means we are going to eliminate the error due to the eccentricity of the wheel by applying the torque in both clockwise as well as in the anti-clockwise directions. Also, we are going to eliminate the errors due to any slipping at the clamped end by obeying by observing the readings at 2 points on the rod. Okay, this is the approximations we are going to do in this method. Okay, so in this method we are actually having the two scales, S1 and S2, and we are measuring the angle. Suppose suppose this wire which we have taking is having the high rigidity, then whatever if you are adding a high loads, the deviation from the zero, which is very negligible or very small. So during that case, we cannot able to accurately measure what is the angle which is actually deviated. So instead of taking this static torsion method, we have another method which is actually called as instead of using the this angle, this two different angle scales, we are going to add we are going to use a mirror and telescope in the apparatus. Okay, so we are going to take the same apparatus model, but instead of taking the circular scales, we are going to add the mirror and scale and telescope. Okay, so you can see the schematic diagram of this scale and telescope, where we have the same apparatus. But instead of taking this scale, we are going to fix the mirror in the scale with the one end. So at the same time, you are going to keep the one telescope in the opposite direction with some difference. Along with this telescope, we also have some meter scale. Okay, so that suppose if you are adding the weights on the hanger, so there is a deviation in this mirror, because the twisting is going to happen, so that the mirror is actually going down or upper. So this reflection of this readings of the scale is actually, the scale is going to be heated in the in the mirror, and then it is actually reflected back to the telescope, so that we can accurately find the reading. Okay, so compared to this method, the method with the apparatus with the scale and telescope is very accurate. Suppose this is a wire which we are going to take, and suppose this is a mirror which we have attached with the wire. Suppose if you are adding a weight in this direction, so that there is a twist in the wire, so that this wire is actually twisted in this direction, so the mirror is actually moving in this direction, for example. So that is suppose this is a reference point, and this is actually moving in this direction, so that there is a theta deviation here. So this theta deviation is actually measured, the scale, this is the scale, so that there is a this is the okay, let's take this as like the figure itself, and the figure itself. So we can see that the wire is here. So this is the actual the reference line without having having the load. Suppose if we are adding the load, then there is twist in the wire with a clockwise direction, there is a theta difference, so that the measure, I mean the scale, the reading of the scale is actually reflected back from the mirror to the telescope, so that we can easily see this in the readings through the telescope, so that we can just find out the corresponding deviation from the original unloading twist to the loaded twist. Suppose we are having a reference point, reference line in the mirror. So this reference line of the mirror is actually focused on the to the telescope. This telescope is adjusted to see the reflected image of the telescope in the mirror, and seen through the we can see the reading through the telescope. So with some dead weight, suppose there is no weight is added, then that is the readings is actually noted in the tabular column. Then once you are actually adding the weight continuously with every 0.5 or every uniform increase in weight, so that there is a deviation in the readings. So instead of directly calculating this theta, you are actually calculating the distance s. So we already know this d, because we already have the distance, the telescope and scale apparatus actually having the placed in the some distance which is taken as a d, and if you know the s, then you can easily calculate the 2 theta. Okay, from this we can easily calculate the theta by 2. The values divided by 2, we can get that as a theta. Once you done the readings on the one direction, then the weights, once you are doing the taking the readings on the adding the weights, then the weights are then decreased continuously in steps of the same 0.5 kg, and then the readings are taken again in the tabular column. So now the torque is in reversed now. By passing the tape in the anti-clockwise direction, that means in the other direction, again you can do again you can take the readings, both the loading as well as unloading. From this readings, the shift of the scale, that is the s, which can be calculated for the every kilograms. Okay, so we know what is the length of the wire, that is taken as the L. This length is actually the length of the wire fixed from the fixed end to the mirror, which is we have actually fixed the mirror attached. Okay, so the radius A can be measured from the screw gauge. So you can measure the radius in the different positions with different places of the rod, so that you can take the average radius. Okay, so that your readings will be very accurate. Again, the radius of the wheel, which we also measured, of the wheel, which is again taken as a capital R, is again calculated. Then we already know the distance between wire and scale telescope, which is again taken as a capital D. Okay, so if all these things, measurements are known, then you can find out the rigidity modulus using the formula 4 times of mg RLD divided by 5 times of a power 4 s. So this s is, instead of taking the theta, we are actually calculating the d and s, so that we can easily calculate the rigidity modulus. So from the rigidity modulus, which is calculated using this method, is actually somewhat accurate than the previous method, because here we have manually taking the readings from the scale. But suppose if the twist is very small, then we cannot able to accurately find out the degree in terms of radians, so that we can use the telescope and the meter scale method, which is somewhat accurate than the previous method. Okay, fine. Now we are going to find out what is the work done in twisting the wire. Okay, So we already know that suppose if you take the same cylindrical wire with the length of L and radius of A, which is one end is fixed with the one end is rigidly fixed and another one is actually twisted through the by adding a weight within some angle by applying a torque at the other end. And we already know that the small c, the capital C, is the torque per unit angle. Torque per unit angle is taken as a C of torque per unit angle of the wire is taken as a C, and so that suppose if you want to the torque required to produce a twist with in terms of with some theta of the wire which is taken as, suppose we taken as some capital C is equal to small c into theta. So this is taken as a small c. So this small c into multiplied by the theta is the torque required to produce the some twist. Okay. So we can also find that suppose if this torque is applied to the wire, the opposite forces are actually stored as a potential energy, so that we can take it as a work done in twisting the wire through a small angle theta, means small angle, let us take it as a d theta is, so we can multiply this in terms of we can d theta at both sides. So c times of d theta, which is equal to small c theta into d theta. So this is that work done work done required to twisting the wire through a small angle d theta. So that we can find out the total work done. The total work done in twisting the wire through an angle the theta, which can be taken as the integration of that piece is taken as W integration of 0 to theta this small t into theta d theta. Okay, so we are going to integrate this equation. We already know that the C is the constant, that means the couple per unit twist is a constant which we can taken outside. So the W is equal to theta into d theta is actually theta squared divided by 2. We already have the theta and 0 as limit. So once we are substituting the upper limit, it is theta squared by divided by 2 and minus 0. So that is the final answer will be equal to half c times of theta squared. Okay, so this is the work done to twist the wire through an angle theta. So you can, this is a potential energy. So we already know that in the mechanics we already find that the potential energy is equivalent to the half times of mv squared. That means suppose if you are having the linear push, suppose we are applying a push in the system, then the potential energy is stored in this body is a half mv squared. So similarly you can twist the wire with some angles. So the work done is equal to half times of c times of theta squared. Okay, which is almost equal to the linear the potential energy which is stored in the body. Okay. Okay, so let's have a let's look into the some problem which is related to the potential energy. Okay, this is the example problem. So we have to find the amount of work done is in twisting a steel wire of radius 10 power minus 3 meters and of length of 0.25 meters through an angle of 45 degree. So the rigidity modulus of the steel is given as 8 into 10 power 10 Newton per meter squared. So we already know that the work done, which is W, is equal to half into c theta squared, and we know what is the value of C, so which is we already calculated. The derived the value of couple per unit twist, the torsion per unit twist, which is equal to pi g a power 4 divided by 2 times of L. So this is the C value. So we can directly substitute this value here, so that we are the work done which we can calculate is half pi g a power 4 theta squared divided by the 2L. So that we get the 4 times of L, that we can take as a 1 by 4 times of this. So that is our value. The given values are, G is equal to 8 into 10 power 10 Newton per meter square, and the A is given as 10 power minus 3 meters. Theta is given as 45 degrees, which we can convert it into the radians, so that 45 pi divided by 45 degrees pi divided by 180, which is equal to pi divided by 4, that is the radians, and then L is equal to 0.25 meters. So all these things we have know, so that W is equal to 1 by 4 times of pi value is 3.1415 into the G value 8 into 10 power 10 Newton per meter square, and the radius is 10 power minus 3 the whole power 4, and the theta, that is theta squared, pi divided by 4 pi squared divided by the length of 0.25. So once you can calculate the value with the calculator, the final value is 0.155 joules. So this is the work actually stored as a potential energy in the corresponding wire. Suppose if you are giving the twist of 45 degree, okay.